Welcome to this next video in which we are discussing unique factorization domains. Okay, so what we're now going to try and prove is that all principal ideal domains are unique factorization domains, and I think this proof is really valuable for giving us good intuition about unique factorization domains and why they can even exist in the first place. Okay, so let's begin. So we'll do it here. So let's say R, to start with, is a principal ideal domain. Okay, so it's an integral domain in which all the ideals are principal. Okay, so there are no ideals which are not generated by a single element. Okay, so that's excellent because we already have the is an integral domain condition met. Okay, so if I just turn back over, remember the conditions for a ring, a non-zero commutative ring, to be a unique factorization domain are that it must be an integral domain and this then factorization condition. So the fact that we're starting off with a principal ideal domain instantly tells us that we do actually have the integral domain condition. So now all we need to worry about is this factorization business. Okay, so what we need to take then is some non-zero element and also a non-unit element, because we know units are just equal to units as far as the prime factorization is concerned. And what we need to show is that we can actually find a prime factorization. So there are two parts to what we need to do. We firstly need to actually show that it even exists, that you can even come up with such a thing, a factorization into irreducibles. And secondly, we need to show that it's unique up to changing the associates around and changing the unit in the front. Okay, so up until that point, it's unique. Okay, so let's take some little r then, that's an element of our principal ideal domain, and as promised this is not equal to the additive identity, neither is it a unit. Okay, so we pick some element that's not the additive identity and is not a unit, and let's now attempt to construct a irreducible factorization, a factorization into irreducible elements. Okay, so either the element that we've got here is an irreducible or it's reducible. Okay, so if it's irreducible, then you are done. Okay, you already have it written as an irreducible, so just make the prime factorization, the irreducible factorization, I should probably say to be utterly rigorous, as 1 as the unit times itself, and there you have a beautiful factorization into irreducibles. Now if it's not irreducible, then it will be instead reducible, and it will be writable as a product of two elements which are not unit elements. Okay, so we'll now assume that R is not reducible, and it can therefore be written as R1 times R2, where neither of these is a unit. Okay, so remember the definition of irreducible is that an irreducible element is an element where if it's written as a product of two other elements of the ring, one of those two things in that product must be a unit. Okay, so if it's not irreducible, then we must be able to find a product of two things which are not units, neither of them is equal to a unit, which gives you this element. Okay, so that's perfectly valid. So I've taken case 2 where it's reducible, and I've now written it as a product of two things, neither of which is a unit. Okay, now we continue on basically. Now we have to ask, is R1 irreducible, is R2 irreducible? Of course, if they're both irreducible, job's done again. Okay, we've now written it as an irreducible times the irreducible, just stick the unit 1 in front of there, and you've now got your factorization into irreducibles. Of course, we then have the possibility that one of them's irreducible, one of them's not irreducible, one of them's reducible instead, or the even worse possibility that both of them are reducible. And then if you do have ones that are left over that are reducible, then you continue this process on. So let's say R1 is reducible here. I won't make a comment on R2. It might be irreducible, it might be reducible. Okay, if R1 is irreducible, sorry, if R1 is reducible is what I mean, I can write it then as a product of two more things, neither of which is a unit. So I'll be able to write it as R11 times R12 here. So I'm now giving it a second index to show that it's coming after the first R1 here. And then my R here will be R11 times R12 times R2. And of course, if R2 is reducible, then you'll also be able to do this for R2. So you'll turn it into R21 times R22 here. Okay, and now you've got a product of 4 things that is going to equal R. And all of these will be non-unit elements if both of these were reducible. Okay, and you just continue on like this. Wherever one wasn't irreducible, you'd then break it up. So let's say quite a few of these were finally irreducible. So let's say R11 was irreducible, R21 and R22 was irreducible. What you then have to do is break up R12. So anything that's reducible, you break up and you say, okay, if it's reducible, then there exists a product of 2 non-unit elements which will multiply together to give R12. So in this case, we'll have R121 and R122 here. Okay, and let's say these two then finally are both irreducible, and then of course our final factorization into irreducible elements would be R11 times R121 times R122 times R21 times R22 here. And of course you put the unit 1 out the front. So there would be our factorization into irreducible elements. Okay, and of course if any of these irreducible elements were the same, you'd group them together and raise the power. Okay, or if they were associates, you'd play around to try and get it into the neatest form, but we have fundamentally got it now as a factorization of irreducibles. So I hope the idea is clear, that you just keep going. Wherever one of the elements is reducible, you just say, okay, split it up into 2 non-unit things, and then just keep going until you eventually get a product of irreducibles. Now, that all sounds fantastic, but there is, of course, one problem that you're probably shouting at your computer screen, okay, which is, how do we know that this process ever terminates? How do we know that this doesn't go on forever? Okay, because you could just continue on like this, getting reducible after reducible after reducible, and just having to continue on, continue splitting it up further and further and further, getting a bigger and bigger product, but never actually get to an end. How do I know that this process terminates? Well, that's where we're going to use the fact that this is a principal ideal domain, and this is the most complicated part of the proof, proving that this does indeed terminate. Now don't worry, it's not too difficult, but it is the big part of the proof, and it's almost analytic what we're about to do, okay, because we are trying to prove that this infinite process cannot be infinite. Okay, so what we need to think about is ideals when we're doing this, okay? So let me explain what I mean. So we have got this element R here, which is not the 0 element and it's not a unit. Okay, so we can generate its principal ideal, and of course we won't get the entire ring because it's not a unit. Okay, only units will generate the entire ring. They are the only ones that will generate the unit ideal. So R will be properly contained within capital R. Okay, now I want to prove that we cannot have this infinite process of splitting down this, into more and more elements. I want to prove that this cannot go on forever. So the way I'm going to do it is I'm going to suppose the opposite of what I want to prove and reach a contradiction. Prove that it's not possible, basically. Okay, so let's suppose that I can go on and on forever. So let's suppose I split R into R1 times R2. Then let's suppose R1 is not reducible. So we split it into R11 times R12. And let's now say that again R11 is not irreducible. So we can then split it down into R111 times R112, and then let's say again R111 isn't irreducible, so we can split it down further. So I'm just, for notational purposes, going to say that all of these ones where its indexes are just 1s are going to be the reducible elements. They're all going to be reducible. So I'll get this sort of infinite tail of elements that are reducible. So I'll have R1, R11, R11, 1, and then R1111. Okay, so I'm going to say that all of these ones where the indexes are all 1s are reducible. Now of course I can do that, it's just notation. Okay, it's just to make it notationally simpler. If the process does indeed go on forever, there will be this infinite trail of reducible elements which can always be split up further. I'm now just saying, for notational reasons, let's just have them indexed simply by R1, R11, R111, etc. Okay, now I want to ask about what I can say about the principal ideals generated by all of these. And you might be thinking, what can you say about it? But I can actually say something very interesting. Okay, so I've already made this comment that the principal ideal generated by R will be properly contained within the entire principal ideal domain. Now let's ask about the principal ideal generated by R1. Well, firstly, I claim that that is going to be properly contained within the entire ring. Now that's very simple because R1 is not a unit, because remember R is, we're supposing, reducible, so we've split it into the multiple or the product of two non-unit elements here. So because it's not a unit, it will be properly contained within the ring capital R, and in fact that goes for all of these. All of these are not going to be units, because remember this is a tower effectively of reducible elements, and we're splitting them down always into more non-unit elements. Okay, so we can say that about all of these, that they're going to be generating principal ideals which will be properly contained in the principal ideal domain capital R here. The other thing that I can say about the principal ideal generated by R1 is that it's going to itself properly contain R. Now why is that? Well, it's because R2 is not a unit. Okay, and that then implies that the principal ideal generated by R1 properly contains the principal ideal generated by R. Now firstly, let me just prove this as a little aside. So if you generate the principal ideal generated by R, it's going to have to be completely contained within the principal ideal generated by R1, because from this line here we can see that R is in the principal ideal generated by R1 because it's R1 times R2 here. Okay, and as soon as one thing is in an ideal, its entire principal ideal has to be in that ideal, so we can therefore say that the principal ideal generated by R has to be contained within the principal ideal generated by R1. What allows me to then say it's properly contained? Okay, well I claim that R1 is not an element of the principal ideal generated by R, and since it is an element of the principal ideal generated by R1, that must mean that this is bigger than this, so this containment must be proper. Okay, now how can I conclude that R1 is not an element of the principal ideal generated by R? Well, let's assume the opposite and prove a contradiction. So if R1 is in here, then R1 would be some multiple of R. So let's just say it would be A times R, where A is some element of our principal ideal domain. Okay, but that's going to lead to a contradiction. The reason being that we can now stick in this expression for R1 here. So we can say that R is going to be A times R2. Then of course you can just rearrange this because we're working in a commutative ring, so it'll be R times A times R2. And then because the principal ideal domain is an integral domain, we can cancel off the R here, because of course we know that it's not equal to 0. That's one of our initial assumptions. So we can cancel it off there, and then we'll get that A times R2 is equal to 1, and therefore R2 is a unit because A is going to be its multiplicative inverse. So there's our contradiction. If we assume that R1 is an element of the principal ideal generated by R, you can prove that R2 isn't a unit, which is not, well, that's rubbish because we assumed that R1 and R2 were not units, okay, because R was assumed to be reducible and therefore could be written as two non-unit elements multiplied together. So indeed, that now shows us that R1 is not an element of the principal ideal generated by R, so this containment must be proper. Okay, now the exact same argument as we've just applied to show that the principal ideal generated by R1 must be properly in between the principal ideal generated by R and the principal ideal generated by 1, the unit ideal here, would apply to R11 with respect to the principal ideal generated by R1 and the entire ring capital R. So what I actually claim is that you can then argue the same thing for R1. So what you can now say is that R11 is going to properly contain the principal ideal generated by R1 and is itself going to be properly contained within the ring capital R. So I've already argued as to why it must be properly contained within the ring capital R, because it's not a unit, and then because this is also supposed to be not a unit because this was supposed to be reducible, then it must be the case that this principal ideal generated by R11 must properly contain the principal ideal generated by R1. Okay, and then you can go on. Okay, so if we had this infinite tower of reducible elements here, you would get this infinite ascending chain of principal ideals where they're all properly contained within the last. So R would be properly contained within the principal ideal generated by R1, which will be properly contained within the principal ideal generated by R11, which would be properly contained within the principal ideal generated by R111, and then it would go on and on and on forever. If this tower went on forever, you'd also have this ascending chain of ideals which would go on forever. And I claim that you cannot have such an ascending chain of ideals in this way in a principal ideal domain. I claim that these properly contained symbols here make this impossible, because these would all be properly contained within one another. Okay, so that's the bit that now is going to require some proof. Why can this not exist? Why can this ascending chain of ideals, which are all properly contained in this way, not actually exist in the principal ideal domain? Okay, so let's get another piece of paper and prove that result. Okay, so I'll need this later, so I'll just put it aside there. Okay, right. So let's now say that we have an ascending chain of ideals within a principal ideal domain. So let's say R is a principal ideal domain, a PID. Okay, and let's say that we have an ascending chain of ideals, but this time I'm not going to assume that they are properly contained within one another. Okay, this is the difference here. Okay, so I'm going to have I1 here, which is going to be contained, but not necessarily properly contained, in I2, which is then going to be contained, but again not properly contained necessarily, in I3, and then it will go on and on and on, so it will be, and again, an infinite chain, an infinite ascending chain of ideals, but we aren't saying necessarily this time that it's proper containment. Okay, so here we are. So I've got an infinite ascending chain of ideals, but I'm not assuming at the moment that it's properly contained. Okay, and indeed we're going to show that it can't possibly be. So what I now want to show is that it must at some point become stationary, this ascending chain of ideals. Okay, and what do I mean by that? I mean that there must be some point in this great big ascending chain, and this is where it gets almost like analysis. There must exist some little n, okay, which we'll index our ideal by, so there must exist some in such that it is the case that for all ideals beyond that, okay, so for all ik where k is greater than or equal to n, it is the case that ik is equal to in. Okay, that's what I mean by stationary. This ascending chain of ideals eventually becomes stationary. They all become constant. Okay, so you just get this same ideal repeated over and over again for an infinite ascending chain, but it becomes stationary. That's what I mean. Okay, and this is going to be true in a principal ideal domain, and of course that would contradict the existence of this ascending chain of ideals where they're all properly contained within one another, because this couldn't possibly become stationary. Okay, so if we can prove that any ascending chain of ideals like this has to become stationary in the principal ideal domain, it contradicts the existence of this, because this is an ascending chain of ideals that never becomes stationary, and that's not going to ever happen in a principal ideal domain, as I'm about to prove. Okay, so how are we going to prove that it has to become stationary in this way? Okay, so what I'm going to consider then is the union of all of these ideals. I'm going to consider a great big infinite union here. So the union from I is equal to 1 to infinity of I, and I'll subscript it I here. Okay, so I'm going to union all of these ideals together, okay, and I'm going to go on and on and on and on and union absolutely all of them, okay, right, and now I'm going to call this thing capital I, and my first claim is that this is actually an ideal. Okay, so when you union together all of these ideals, this infinite number of ideals, you get another ideal. And note there's a very important point here. You might be thinking, wait, if you union together ideals, do you end up with another ideal? But there's a big important thing you have to remember here. The containment. They're all contained in the one that's after them. Okay, that's why the union of this actually makes an ideal. Okay, if you were just unioning a whole bunch of ideals, you wouldn't necessarily at all end up with an ideal. It's the containment that makes this true. Okay, so let's prove this firstly. So in order to check that this is an ideal, we firstly need to check that it's an additive subgroup in our principal ideal domain, and then we need to check that it's closed under multiplication. So let's start with additive subgroup then. Okay, so to prove that a subset is a additive subgroup, we need to make sure that it obeys closure firstly, so that when you add two elements together, the answer is back within the subset. Okay, we also need to make sure that it obeys the fact that we have the additive identity in there, and we also need to check that it has additive inverses in there. We don't need to worry about associativity, and we don't need to worry about commutativity. We get those automatically because it's a subset with the inherited addition law on it. Okay, so let's start with closure. So axiom number 1 of proving it's a subgroup then. Okay, we want to make sure that if we have two elements from here, so let's say we have A and B, which are an element of this subset capital I here, we want to prove that A plus B is also going to be in our subset capital I here. So how can we do that? Well, if A and B are in the ideal capital I, then they must both be contained within ideals that we're unioning up here. I have difficulty saying unioning. Okay, so if A and B are in this subset capital I here, it must be the case that each of these is contained within one of these ideals. So let's say A is in the ideal, let's say I, and I'll just subscript it A for now, and B is in an ideal, let's call it IB. Okay, now you might then have difficulty in deciding whether A plus B is going to be in I, because of course if it was the case that both of them were in the same ideal, then we could conclude that A plus B was in I, because we would be able to conclude that it was in that ideal, but we've now got them in separate ideals. Okay, but then we have to remember the fact that they are contained within one another. Okay, so each of these will appear at some point in this chain. Okay, this ascending chain. Just take the one that is further along. Okay, so let's say IB here, the ideal which contains B, is further along. So let's say the ideal which contains B is further along than the ideal that contains A in this ascending chain. Okay, so that would then imply that the ideal containing A was completely contained within the ideal containing B, okay, because B was further along in the ascending chain. And of course that now implies that A is an element of the ideal containing B, and therefore we have an ideal which contains both of them. Okay, now because the ideal containing B here, IB, is an ideal, then it will be an additive subgroup, so A plus B will be in there, and therefore when we union them all together, A plus B will end up in our final subset capital I. So there's your proof that A plus B will have to be in there. Okay, so we don't need to worry about axiom number 3 of a subgroup, or rather of a group, so we don't need to worry about axiom number 2, associativity of a group, so let's skip that one out and go on to axiom number 3 here. So we want to make sure that the additive identity 0 is an element of our subset capital I. Now of course that will be true, because in each one of these ideals you will have to have 0, because they're all the additive subgroups, so of course when you union them all together, you will end up with 0 in the final answer. That's very easy. And now what we want to make sure of is additive inverses, so we want to prove that if A is an element of this subset capital I, that the additive inverse of A is an element of this subset capital I. Okay, now how can we show that? Well, if A is an element of the ideal capital I, then A must be contained in one of these ideals that we've unioned together to get I. So let's say A is an element of the ideal that contains A here, IA. Then of course, because this is an ideal, then it's an additive subgroup, so negative A must be contained within there as well, okay, and therefore negative A will be contained within the ideal capital I, or ideal to B capital I, because that's the union of all of them. Okay, so indeed you do have additive inverses, so that's all good. Okay, so we now have proven that this subset that we end up with, capital I, which is found by unioning together all of these ideals in this ascending chain of ideals, is going to actually be an additive subgroup. So now let's move on to axiom number 2 here, and I'll put this here to save paper. Okay, so move it down a little bit. We want to make sure that it's closed under multiplication, so we want to make sure that you take any element of this subset, so let's say for all I is an element of for all A is an element of capital I, you can multiply it by anything in the larger ring. So for all little r is an element of capital R, it must be the case that r times a is also going to be in this subset capital I. Okay, that's what it means to be closed into multiplication. Now, of course, we're working in a commutative ring, so we don't need to worry about doing it both ways round, so we just need to do it one way round. Okay, now this is very simple. If A is an element of this subset capital I, then that implies that A has to be in one of the ideals that we unioned together to get capital I. Okay, again, we'll use the same notation. A is going to be an ideal called IA here. And then because this is an ideal, R times A is going to have to be in the ideal I subscript A here. And therefore, because we're unioning all of these ideals together to get capital I, R times A must end up in capital I. So indeed, it is going to be closed under multiplication. So it's very nice and easy to prove that this subset that we end up with by unioning together this ascending chain of ideals is going to be an ideal itself. Okay, so how does that then prove that this ascending chain of ideals has to become stationary? Well, it's now where we use the fact that this is a principal ideal domain, because you'll have noticed that at no point so far have we used the fact that this is a principal ideal domain, but now we are going to use the fact. Okay, so because this is a principal ideal domain, this ideal capital I must be a principal ideal generated by some element. Okay, so let's call this element that generates it alpha. Okay, so let's say some element alpha generates this ideal capital I. Now, what we can therefore conclude is that alpha is an element of this ideal capital I, so that's obvious. So alpha is certainly going to be an element of capital I, and if alpha's in there, then it must be in one of these ideals that we've unioned together to get I. Okay, so that must imply that alpha is in one of these ideals at some point. So let's say alpha is in an ideal, and let's call it IN. So you go up to some little n, and indeed this is going to end up being the same little n as up here. So you go up to some little n, and you find that alpha is in that ideal. Okay, and of course, the instant alpha's in there, the entire principal ideal generated by alpha has to be in there. Okay, because it's closed under multiplication, so all multiples of alpha have to be in there. So now that implies that the entire ideal capital I is contained within the ideal capital IN here. Okay, but of course IN cannot be bigger than I, because I is the union of all of the ideals here. So if IN was bigger than I, that's rubbish. IN has to be contained within I because of the fact that you union together all these ideals to get capital I. So we then arrive at the fact that I must equal IN. Okay, and we therefore see that all of the ideals after that have to also just be equal to this IN. Okay, because if any of them were bigger than IN, then I would end up bigger than IN. Okay, so we've now hence proven that this does indeed have to become stationary. You cannot continue getting bigger and bigger ideals infinitely in a principal ideal domain. It must eventually stop. Okay, so an ascending chain of ideals must become stationary at some point. Okay, so that then contradicts this, okay, because if we do indeed have this process of splitting our element down into more elements in this way, going on forever, so we have this infinite tower of reducible elements in this way, we have shown that this gives rise to this infinite ascending chain of ideals that never becomes stationary because all of these are proper containments. Okay, so it would never ever become stationary, and that's a contradiction because this is a principal ideal domain. So this thing cannot exist, and that implies that this infinite tower of reducible elements cannot exist. This process cannot go on forever, otherwise it would give rise to this, which is unfeasible in a principal ideal domain. Okay, so that's how we prove that this must terminate at some point. Okay, if you do this process, you do finish it. Okay, I can't say how long it will take you. It might take you a very long time, but it will not take you forever. It will eventually finish. Okay, this process does terminate. So then you can split any non-zero, non-unit element of this principal ideal domain down into a factorization in terms of irreducible elements. So there is the proof that these factorizations into irreducible irreducible elements exist, in the next video what we will do is prove uniqueness up to the fact that you have associate elements and units can change as well.